Now let us see this example. Design a Moore machine to find the ones complement of a given binary number. We know what is a binary number. A binary number is made up of zeros and ones. So let me have a binary number like this, 1011. So binary number contains zeros and ones. So here sigma, that is input alphabet, contains 0 and 1. Here what is the what we need to find? We have to find ones complement of the given binary number. So what is ones complement? Ones will be converted to zeros and zeros will be converted to ones. So here we have 1. So this 1 will be converted to 0. 0 will be converted to 1. 1 will be converted to 0. 1 will be converted to 0. So output alphabet also contains zeros and ones. Output alphabet is represented by delta symbol. So delta is equal to 0 and 1. So now let us design the Moore machine. Here we can solve this problem by using two methods. The first method is by taking 3 states. The second method is by taking 2 states. Now let us solve the problem in the two methods. So method 1, by considering 3 states. By considering 3 states, let the initial state is Q0. Initial state is Q0. Let output of Q0 is 0. We can take output of Q0 as either 0 or 1. According to that, we can change the transitions. Let output of Q0 is 0. Next, here if we pass, if the input is 0, then we will get a state called Q1. So Q1 accepts 0 as the input. If input is 0, then what is the output? 1. So the output of Q1 is 1. Likewise, we need one more state. That state is Q2. Q2 accepts 1 as the input. If the input is 1, then that input will be passed to the Q2. If the input is 1, then what is the output? 0. So the output of Q2 is 0. Next, Moore machine and Mealy machines are nothing but DFAs. So each state must use the symbols present in the input alphabet. So here on Q0, 0 is applied as well as 1 is applied. If 0 is the input, then 1 is the output. If 1 is the input, then 0 is the output. Now we have to apply input symbols such as 0 and 1 on Q1 and Q2. Here what is the output of Q1? 1. When we will get output as 1? If the input is 0. If the input is 0, then we will get output as 1. If the input is 0, then we will get output as 1. Next, here output of Q2 is 0. When we will get output as 0? If the input is 1. If the input is 1, then the output is 0. Okay. Next, we have to apply 0 on Q2 as well as 1 on Q1. Here output of Q1 is 1. So when the output will be 1? If the input is 0. So if we apply 0 on Q2, then we will get 1 as the output. So likewise, here output of Q2 is 0. So when output is 0, if the input is 1. So if we apply 1 on Q1, we will get 0 as the output. So now Q1 has transitions on 0 and 1. Q2 uses a 0 symbol as well as 1 symbol. So this is the Moore machine for solving this problem. Now let us check whether this machine is correct or not. So for that, let us take an input string. Let the string is 1011. So 1011 means what is the output? 0100 is the output. So initially we are at Q0 state. Initially we are at Q0 state. So Q0 on 1, Q0 on 1 goes to Q2. Next, Q2 on 0, Q2 on 0 goes to Q1. Next, Q1 on 1, Q1 on 1 goes to Q2. Q2 on 1 goes to Q2. What is the output of Q0? 0. Output of Q2? Output of Q2, 0. Output of Q1? Output of Q1 is 1. Output of Q2 is 0. Output of Q2 is 0. We know that in Moore mission, if the size of the input string is n, then the size of the output string will become n plus 1. Here the input string size is 4, whereas the output string size is 5. So here there is no need of this 0. So we have to neglect this 0. So here the output is 0, 1, 0, 0. So 1 is converted to 0, 0 is converted to 1, 1 is converted to 0, 1 is converted to 0. So in this way we can design the Moore mission for solving this problem. Here Moore mission means output is same irrespective of the input. Here output of Q0 is 0, whether we apply 0 or 1. Likewise the output of Q1 is 1, whether we apply 0 or 1. Likewise output of Q2 is 0, when we apply either 0 or 1. So that's why in Moore mission we have to specify the output within the state. Now let us see the second method. The second method is the most efficient method by taking two states. So method 2, by taking two states. Here we have only two states. We know that Moore mission or Mealy mission doesn't have any final state. So here we will have only initial state. We don't have any final state. Okay. Let the second state is let the first state is Q0. Let the output of the Q0 is 0. It is our choice. We can take 1 also. There is no problem. Let here the output is 1. Let the output of Q0 is 0 and output of Q1 is 1. When the output will be 0? If the input is 1. If the input is 1, then only output will be 0. Okay. Next here, 1 is applied on Q0. Now we have to apply 0 on Q0. 0 on Q0 means we will go to Q1. Q1 output is 1. Okay. So this is 1's complement. 1's complement means 0 will be converted to 1. So 0 on Q0, we will go to Q1, output is 1. Likewise here, output of Q1 is 1. When the output is 1, if the input is 0. If the input is 0, then only output is 1. Now we have to apply 1 on the Q1. So 1 means the output should be 0. So we can make the transition to Q0. So 1 on Q1 means it will goes to Q0, output is 0. So this is the Moore mission for solving this problem with the help of the two states. So 0 and 1 are applied on both the states. Now let's check whether this mission is correct or not. So for that, let us take the input string 1011. So initially we will be at Q0 state. Q0 on 1 means Q0 only. Next to Q0 on 0, Q1. Q1 on 1, Q1 on 1, Q0. Next to Q0 on 1, Q0 on 1, Q0 only. Okay. What is the output of Q0? 0, 0, 0, 0. What is the output of Q1? 1. So here Moore mission means here we have to neglect this bit. If the input is 4, here we are getting n plus 1 as the output. So we can neglect this leftmost bit. So the output is 0, 1, 0, 0. So 1 is converted to 0, 0 is converted to 1, 1 is converted to 0, 1 is converted to 0. So in this way we can solve the problem. Now let's see this example. Design a Moore mission that counts the occurrences of the sequence ABB in any input string over A comma B. So here input alphabet mainly contains two symbols. They are sigma is equal to A comma B. Here we have to find out how many times ABB is present in the given string. the number of occurrences of ABB in the given string. Let the string is like this, ABA. So in this, here we don't have ABB sequence. So the output is 0. Let we have a sequence like this, ABB. So one time ABB is present. Let we have a sequence like this, ABB, B, ABB. So one time. So 2 times. So we have to perform some operation on the number of occurrences. So here the output alphabet mainly contains 2 symbols. So delta is equal to 0, 1. So 0 means that sequence is not found. So 1 means that sequence is found one time. So simply we have to add these values. Okay. So that is about output alphabet. Now we have to construct the DFA. So more emission is nothing but constructing the DFA only. More emission or mill emission is nothing but constructing the DFA only. Okay. So here the sequence contains 3 symbols ABB. So if this the size of ABB is 3. So here the DFA totally contains 3 plus 1. Totally DFA contains 4 states. So the states of the DFA are 4. So first one is Q0. Next one is Q1. Next state is Q2. Next state is Q3. We know that in more emission we have only starting state. We don't have any final state. Okay. Next here, what is the sequence? ABB is the sequence. ABB is the sequence. If the sequence is ABB, then simply we have to display the output as 1. Whereas if the sequence is not ABB, then let us display that sequence as 0. So 0 means that sequence is not found. So 1 means that sequence is found. Now we have to make this as the DFA. What is DFA? Each state must uses the symbols present in the alphabet. Here the input alphabet mainly contains 2 symbols, A and B. So in each state we have to uses A and B. So on Q0 A is applied. Now we have to apply B. Here the sequence contains ABB. But before ABB we can have any number of Bs. So there is no problem. So on Q0 A is applied as well as B is applied. Now we have to apply A on Q1. A on Q1. Here what is the sequence? ABB is the sequence. So if we apply the self transition like this, so we can have ABB. So after A, we may have ABB sequence. So in those situations, this is helpful. Next, so on Q1, A is applied, B is applied. Next, on Q2, B is applied. Now we have to apply A. Now we have to apply A. Here what is the sequence? ABB is the sequence. So if we make a transition like this, on A, ABB. So after AA, we may have ABB. So in those situations, it will be accepted. The sequence will be helpful. Next, we have to apply both A and B on Q3. Both A and B on Q3. So if we apply A here, so simply like the previous one, we can go from here to here. So A, after A, we can have BB. So ABB sequence. And next here, we have to apply the B. So we can make a transition like this. So after B, we can have ABB. After B, we can have ABB. So this is the more mission. So what is the difference between more mission here? The difference between more mission and mill emission is, in more mission, each state has an output irrespective of any input. That output is same only. So here the output of the Q0 is 0, irrespective of it may be either 0 or 1. Likewise, the output of Q1 is 0, irrespective of input A, irrespective of input is either A or B. Okay. So DFA means we don't have any output here. DFA doesn't produces any output. Whereas more mission, mill emission means it produces some output. So this is the more mission. Now we have to check whether this is valid more mission or not. So for that, let us take an input string. Let the string is ABB. Let the string is ABB. So ABB here, what is the sequence here? ABB is the sequence. So ABB occurs one time. Now let's check whether we are getting that output or not. So first we always starts from the initial state, that is Q0. Q0 on A. Q0 on A goes to Q1. What is Q1 output? 0. what is Q0 output? 0 only. Next, Q1 on B goes to Q2. Q2 output is also 0. Next, Q2 on B goes to Q3. What is Q3 output? 1. So here we have the sequence ABB. So that's why we got 1 as the output. So with this we can conclude that ABB occurred one time in the string. Now let us take one more string. Let the string is like this: ABB, B, ABB, ABB, BB, ABB. So ABB, this is one sequence, this is one sequence, this is one sequence. So after this sequence we will get 1 as the output. After this sequence we will get 1 as the output. So 1 plus 1 means 2. So we can say that 2 times it appears. Now let's check whether it is correct or not. Q0, output of Q0 is 0. Q0 on A means Q1. Q1 output is 0. Next, Q1 on B means Q2. Q2 output is 0. Q2 on B means Q3. Q3 output is 1. So here we have the sequence ABB. So that's why here we got 1 as the output. Next, Q3 and B. Q3 and B means we'll go to Q0. Q0 output is 0. Next, Q0 on B. Q0 on B means Q0 only. So 0 is the output. Q0 on A means Q1. Q1 output is 0. Next, Q1 on B means Q2. Q2, what is Q2 output? Q2 output is 0. Next, Q2 on B means Q3. Q3 output is 1. So here we have the sequence ABB. So that's why we got 1 as the output. So with this we can say that so ABB occurred twice in the input string. Now let's see this example. Design a Moore machine that prints A whenever the sequence 01 is encountered means occurred in any input string. So here the sequence is 01. So that means input alphabet contains zeros and ones. Whereas what is the output alphabet? It prints A. So we can have A and B. So if the sequence is 01, then it prints A. If we don't have 01 sequence, then it print 10. Okay. Then it print B. Let the sequence is 10. So in this occasion, we will get B as the output. Whereas if we have 01 sequence, then it will print A as the output. So first we have to construct the DFA, and then we need to convert the DFA into Moore mission. And after that we have to check whether that mission is valid or not by taking some input string. Here the sequence contains 01. So 01 length is 2. So we require 3 states. So they are Q0 is the initial state. Next state is Q1. Let us take somewhat bigger circles. Why? Because Moore mission means we have to represent output also in the corresponding state. So Q0 state, Q1 state, Q2 state. So Moore mission means we don't have any final state, but the initial state is Q0. Input is 01. If the sequence is 01, then we have to print A as the output. Otherwise, B is the output. So Q0 output is B, Q1 output is B, Q2 output is A. Now DFA means each state must uses all the symbols present in the alphabet. Here the alphabet has 2 symbols, but on Q0 we have applied only 0. So now we need to apply 1. Before this 01, we can have any number of 1s. So there is no constraint on that. Next, on Q1, 1 is applied. Now we have to apply 0. If we apply 0 here, then what will happen? This will become 01. 01 is nothing but sequence only. So we can apply a self transition like this. So on Q1 also 0 is applied as well as 1 is applied. Next, on Q2 we have to apply 0 as well as 1. Now let us apply transitions on Q2. So we need to apply 0 transition as well as 1 transition. So if we make a transition like this, after 0, 0, 1. So 0, 1, this is the transition. This is the sequence. So let the transition is like this. So 1, 0, 0, 0, 1. Okay. So 1 we will be at Q0 only. 0 we will move to the Q1. Q1 on 0 means we will be at Q1 only. Next again 0 means we will be at here only 1 means we go to the state. So after this let we have one more 0 1. So 0 means we will go to the Q1, again we have 1. Next here from Q2 we can make a transition like this. Why? Because after 1 we can have 0 1. After 1 we can have 0 1, but here after 0 we can have 1. After 0 we can have 1. So the sequence will become 0 1, but here we have to apply 1. So after 1 the sequence is 0 1. Okay, so this is the More mission. Now let's check whether this is correct or not by taking some input string. Let us take 1 0 1 0 0 0 1. So let we here initial state is Q0, so we have to start from Q0 only. So Q0 on 1 means Q0 on 1 means Q0 only. Next Q0 on 0 means Q1. Q1 on 1 means Q2. Q2 on 0 means Q1. Q1 on 0 means Q1. Q1 on 0 means Q1. Q1 on 1 means Q2. The output of Q2 is 1. The output of Q2 is 1, whereas the remaining states output is 0 only. Q0, Q0, Q1, Q1, Q1 output is 0 only. Here we have 0 1 sequence, so that's why we got 1. Here also we have 0 1 sequence, so that's why we got 1. So with this we can say that 1 plus 1 means 2. So 2 times 0 1 sequence is present in the string. So in this way we can solve this problem. Now let us see this example. Design a More mission that takes set of all strings over 0, 1. So that means input alphabet sigma is equal to 0, 1 and produces A as the output if input ends with 1 0. So the output is A if the input ends with 1 0, or produces B as output if input ends with 1 1, otherwise the output is C. So otherwise output is C. So here what is the output alphabet? Output alphabet mainly contains 3 letters A, B, C. So delta is equal to A comma B comma C. So now let us draw the More mission. We know that More mission is nothing but DFM only, but here each state has some output. So here each string contains how many letters? 2 letters. So what is the size of 1 0 or 1 1? 2. So we require 2 plus 1, that is 3 states. First let us draw the diagram for 1 1. So Q0. Yeah, for space constraints I am erasing this portion. So output is A if the input ends with 1 0. Output is B if the input ends with 1 1. C otherwise. So here if you take 1 0 or 1 1, here the string contains 2 letters. So 2 plus 1, totally we require 3 states. So Q0 is the starting state, whereas the remaining 2, let us draw in big circle. Why? Because More mission means we have to specify the output within the circle only. Next to Q1, next to Q2, next to Q2. If input ends with 1 1, then what is the output? B is the output. If input ends with 1 1, then B is the output. Whereas if the input ends with 1 0, then A is the output. So here we have 1. Let us take one more state here. Let the next state be Q4. So here what is the transition? 1 0. If the input ends with 1 0, then what is the output? A is the output. Okay. Otherwise the output is C. So output of Q0 is C. Output of Q1 is C. If the input ends with 1 1, then the output is B. If the input ends with 1 0, then the output is A. Otherwise output is C. Now we have to make this as DFA. So DFA means each state must use all the symbols present in the alphabet Here the input alphabet mainly contains two symbols, 0 and 1. So we have to use those two symbols. Input alphabet symbols are 0, 1, whereas output alphabet symbols are ABC. Here before 1, 0 or before 1, 1, we can have any number of zeros. There is no problem. Here on Q0, 1 is applied. Now we have to apply 0 on Q0. So before 1, 1 or before 1, 0, we can have any number of zeros. There is no problem. If you take Q1, on Q1, 1 is applied as well as 0 is applied. Next we have to apply 1, 0 on Q2 as well as 1, 0 on Q4. So let us apply 0 on Q2 first, 0 on Q2. So if we apply 0 on Q2, then where we can go? Here 0 means 1, 0. So there is no use here. Yeah, here we have 1, 0, 1, 0. So here we have 1. After that, if we have 0, then the output is A. So 1, 0 means if the input ends with 1, 0, then the output is A. Okay. Here we have 1. So if we have 0, then establish a connection like this. Suppose if the string is like this, 0, 1, 1, 0. So 0 means we will be at Q0 only. So 1 means we will go to the Q1. So 1 means we will go to the Q2. Next 0 means we will go to the Q4. Output is A. Okay. Why? Because here the string is ending with 1, 0. Okay. Next we have to apply 1 on Q2. 1 on Q2. Here 1, 1. Here we can apply any number of ones. There is no problem. Why? Because if the input ends with 1, 1, then the output is B only. Output is B only. So we can apply the self transition. There is no problem. So on Q2, 0 is applied as well as 1 is applied. Now we have to apply 0 and 1 on Q4. 0 and 1 on Q4. So if we apply 0, 1. Yeah, if we apply 1 here. If we apply 1 here, after this 1, we can have another 1. So that we will get B as the output. So we can make a connection like this, 1. Why? Because if the string is like this, 0, 1, 0, 1, 0, 1, 1. Here the string is ending with 1, 1. So output should be B. So 0 means we will be at Q0 only. So 1 means we will move to the Q1. 0 means we will go to the Q4. So 1 means Q4 to Q1. 1 means Q2. So output is B. So 1 is applied. Now we have to apply 0. Now we have to apply 0. 0 on Q4. So 0 on Q4 means there is no other possibility. So we can make a connection like this. So after 0, we can have 1, 1. So we will get B as the output. So this is the Moore emission in order to solve this problem. Now let's check whether this Moore emission is correct or not. Let we have a string like this, 0, 0, 1, 0. So here the string is ending with 1, 0. So it has to produce A as the output. Initially we will be at Q0 state. Q0 on 0 means we will be at Q0 only. Next Q0 on 0 means we will be at Q0 only. Next Q0 on 1 means we will go to the Q1. Next Q1 on 0 means we will go to the Q4. So what is the output of Q0? C, C, C. What is the output of Q1? C. What is the output of Q4? A. So here we have 1, 0 pattern. It is ending with 1, 0. So that's why here we are getting A as the output. Now let's take one more string which ends with 1, 1. Which ends with 1, 1. Let me have a string like this, 0, 1, 0, 1, 0, 1, 1. So here the string is ending with 1, 1. So we have to produce B as the output. So initially we have to start at Q0. So Q0 on 0 means Q0 only. Q0 on 1 means Q1. Q1 on 0 means Q4. Next Q4 on 1. Q4 on 1 means Q1. Next Q1 on 0 means Q4. Next Q4 on 1 means Q1. Next Q1 on 1 means Q2. Here the string is ending with Q2. What is the output here? Here we are getting B as the output. Now let's check the third scenario. The third scenario is If the string doesn't ends with 10 or 11, it has to produce C as the output. So now let us take that scenario. Let we have a string like this 0 0 1. Here the string is not ending with 10 or 11. So we have to produce C as the output. So Q0 on 0 means Q0. Q0 on 0 means Q0. Q0 on 1 means Q1. So we are getting C as the output. So in this way we can solve this problem. Now let us see this example. Design a Moore mission to determine residue modulo 4 for binary number. So here the input alphabet sigma is equal to, it is a binary number. We know what is a binary number. Binary number is a collection of zeros and ones. Here we have represented the decimal digits from 0 to 10 in binary notation. So 0 means all zeros, 1 means 0001, 2 means 0010. Likewise we have represented up to 10. So sigma is equal to 0 comma 1. And here our target is to perform residue modulo 4. So what is the modulo? If we divide any number with 4. If we divide any number with 4, then the modulo which we will get is, modulo means remainder. The remainder which we will get is 0 or 1 or 2 or 3. Maximum we will get these 4 digits only. So the output alphabet delta is equal to 0 comma 1 comma 2 comma 3. Why? Because maximum we will get these 4 reminders only. Let us consider 0 1 2 3. So what is the modulo of 0 modulo 4 means 4 zeros are 0. So 0 minus 0 means 0. So 0 modulo 4 means 0. Likewise 1 modulo 4 means 1. 2 modulo 4 means 2. 3 modulo 4 means 3. So maximum we will get these 4 digits only. If we consider any number, let us take 72. What is the result of 72 modulo 4? So 4 72. 4 ones are 4. 7 minus 4 3. So 4 18s are 32. So 0 is the result. Okay. Now let us solve the problem. So here we have to design the Moore mission. Here we have output alphabet contains 3 symbols. So maximum here in this problem we require 4 states. The first state is Q0. The first state is Q0. The output of Q0 is 0. Next state is Q1. Output of Q1 is 1. Next state is Q2. Output of Q2 is 2. Next state is Q3. Output of Q3 is 3. Moore mission is nothing but constructing the DFA only. We know what is DFA. DFA means each state must use all the symbols present in the alphabet. Here the input alphabet contains 2 symbols. So each state must use 0 and 1 symbols. Okay. Now let us consider the first one. The first digit is what? 0. So how we will get 0? 0 means 4 zeros. What is the result of 0 modulo 4? 0 modulo 4 means 0 only. So 0 means here we have to get output as 0 only. Q0 output is 0. 4 zeros means let us write the self transition. So if we apply 4 zeros, then we will be at Q0 only. Output of Q0 is 0. And now let us consider 1. What is the result of 1 modulo 4? 1. So if we apply 0 0 1, then we have to get output as 1. So 1 means output of Q1. Okay. So we need to be at Q1 state after performing this operation. So 000 means we can apply 000 here. Next, if we apply 1, then we will be at Q1 state. Output of Q1 is 1. Now let us consider 2. So 2 means 0010. What is the result of 2 modulo 4? 2 modulo 4 result is 2. So if we perform 0010, then we have to be at Q2 state. Why? Because Q2 output is 2. So what is the input here? 0010. So 00 means Q0 state. So 1 means Q1 state. If we apply 0 on Q2, if we apply 0 on Q2, then we will be at, if we apply 0 on Q1, then we will be at Q2 state. Output of Q2 is 2. Now let us consider 3. So 3 means 0 0 1 1. 3 modulo 4 means 3. So if we apply 0 0 1 1, then we need to be at Q3 state. So 0 0 1 1. So 0 0 means if we apply 0 0 on Q0, we will be at Q0 only. If we apply 1 on Q0, then we will be at Q1. Next, if we apply 1 on Q1, then we need to be at Q3 state. Q3 state. So if we apply 1 on Q1, then we need to be at Q3 state. Now let us apply 4. So 4 means 0 1 0 0. 4 modulo 4 result is 0. 4 modulo 4 result is what? 0. So if we apply 0 1 0 0, then we need to be at Q0 only. So Q0 on 0 means Q0. Q0 on 1 means Q1. Q1 on 0 means Q2. 0 1 0 0. Next Q2 on 0 means we need to be at which state? Q0 state. Why? Because 4 modulo 4 result is 0. So we can make a transition like this. So 0 1 0 0. Next 5. 5 modulo 4 result is 1. So if we apply 0 1 0 1, then we have to get Q1 state. 0 1 0 1. So 0, next 1, next 0. Next if we apply 1, then we have to be at 1 state. So here the transition, we can write the transition like this. 0 1 0 1. Okay. So that is 5. Okay. Next 6 means 0 1 1 0. Output of 6 modulo 4 is 2. So we need to be at Q2 state if we apply 0 1 1 0. So 0 1. So 1, next 0. We need to be at Q2 state. So we can make a transition like this. So 0 1 0 0 1 1 0. Next 7. 7 means 0 1 1 1. For 7 modulo 4 means 3. 3. So we have to be at Q3 state. If we apply 0 1 1 1. So 0 1 1. So if we apply one more 1, then we have to be at this Q3 state only. So we can apply self 1. So 0 1 1 1. Next 8 means 1 0 0. 8 modulo 4 result is 4 2s are 8 0. So we need to be at Q0 state. So what is the input? 1 0 0. 1 0 0. So 1, next 0, next 0. So self loop is 0. So this is already applied. 1 0 0. 1 0 0. So 1 is applied. Next, if we apply 1 on Q0, then we'll go to the Q1. Q1 on 0 means Q2. Q2 on 0 means Q0. Q0 on 0 means Q0. So this is already over. Next 9 means, what is 9 modulo 4? 4 2s are 8, 1. So we have to be at output 1. So if we apply 1 0 0 1. So 1 0 0 1. So this is also over. Let us check the last one. 1 0 1 0. So 10. 10 modulo 4 means 2. So if we apply 1 0 1 0, then we have to be at 10. So 1 0 1 0. Next 1 0. So if we apply 1 on Q2, again Q1, next 0 means Q2. So we got 2. So now let us check whether we have applied 0 1 inputs on each and every state or not. If we don't apply, then we have to apply them. So Q0 on 0 is over. Q0 on 1 is over. Next Q1 on 0 is over. Q1 on 1 is over. Q2 on 0 is over. Next Q2 on 1 is over. Q3 on 0 is over. Q3 on 1 is over. So this is the Moore mission for solving this problem. Now we have to check whether this Moore mission is correct or not by applying some input string. Let us take 2 examples. Let the first input string is 15. So what is the result of 15 modulo 4? So 4, 15, 4 3s are 12. 15 minus 12 means 3. So remainder is 3. So we have to get this Q3 state as the output. So let us represent 15 in binary notation. 15 means 8 plus 4 plus 2 plus 1. So 4 bits are enough. So 4 ones. So initially we have to be at Q0 state. So Q0 on 1 means Q1. Q1 on 1 means Q3. Q3 on 1 means Q3. Q3 on 1 means Q3. What is the output of Q3? 3. So that is the result only. Okay. So we can say that this mission is correct. Now let us check one more example. Let the string is 1010. 1010 means 10. What is 10 modulo 4? 2. So we need to be at Q2 state. Let us check whether we are getting this one or not. That one or not. Q0 on 1 means Q1. Q1 on 0 means Q2. Next Q2 on 1 means Q1. Next Q1 on 0 means Q2. What is the output of Q2? 2. So that is nothing but 10 modulo 4 only. So we can say that this Moore mission is correct only. So in this way we can design a Moore mission to determine residue modulo 4 for any binary string.